Good morning and welcome to Tech 259 on Monday, April 26th, 2021. Today is actually the last day when we'll be talking about new material in this class. When we have our Zoom session on Wednesday, we'll be talking about a review of all the material that we've covered in the second half of this class and about the last exam that'll occur during finals week. We'll talk more about the format and structure and topics for the last exam when we meet on Wednesday. So today we're going to continue our discussion of energy storage. When we met on Zoom last Wednesday, we talked about batteries. And in that discussion, we spent some time talking about how batteries are really useful and versatile, but they don't really have the highest power density and they don't have the highest energy density. They're just pretty good at lots of things, which makes them useful and versatile. And today we're going to talk about some different types of energy storage because batteries aren't the only kinds of energy storage. And we showed and talked about a long list of kinds of energy storage last week when we met. And we don't have time to talk about every single kind of energy storage in this class. That would take a long, long time. So to abbreviate things a little bit, I've picked what I think are some of the best things to talk about in terms of types of energy storage. And the ones I've picked are some combination of useful and commonly used and things that I think maybe you haven't seen before in other classes, like you haven't studied them in depth in Tech 160, for example. So I've picked a couple of types of energy storage that we'll talk about in a little bit more detail today. And to do that, I'm going to switch over to my slides.
All right, so don't worry, it's not the same presentation. This is the same slide as I showed last time. Let me get a pointer. There we go. All right, so this is one of the same slides as I showed last time, just to point out how many different types of energy storage there are. And I'm certain that this is not an exhaustive list either. You could probably come up with more types of energy storage. But this is a pretty good list of different types of energy storage. And we're going to talk about several of them today. And the ones that we're going to talk about today are, first we'll talk about flywheels. And then we're going to talk about compressed gas. And then we're going to talk about gravitational energy storage. So we're going to talk about a bunch of these different mechanical types of stored energy. I think you probably at least briefly studied pumped hydroelectric in Tech 160, I believe. So I'm not going to say a whole lot more about it right now. There's pumped hydroelectric. The brief amount that I will say about it is it has some big advantages. There's a huge amount of energy that you can store in pumped hydroelectric. But the big disadvantage is that you need a very specific set of geographical circumstances. You need to be in hilly country and just kind of happen to have some reservoirs that work out very nicely. So you won't find that in Illinois or kind of anywhere in the Midwest, really. Pumped hydroelectric doesn't really work out very well for mainly the geography reason in the Midwest. So I'm not going to say much more about pumped hydroelectric. We'll talk about these different types. Mainly because I feel like we've already talked quite a bit about thermal energy. So you probably get the gist of all of these just from our discussion in the first half of the semester. And a bunch of these, well, we've talked about batteries last time. Capacitors, I'm not going to say a whole lot about that. Basically, they store energy in the form of an electric field. And you can get power from them very rapidly. So their power density, the amount of power that you can get per, say, unit volume or per unit mass is pretty good, but their energy density is poor. In other words, you can't store a whole lot of energy in them, but you can get a lot of power out of them very quickly. So capacitors tend not to be real economical or effective if you want to store a lot of energy. So you will not see very many electric vehicles using capacitors for energy storage, although I think there are one or two, but not very mainstream. Fuel cells, so this uses hydrogen mainly as a fuel. and they're still not exactly real mainstream, although they've been getting more common in the past decade or two. Biofuels, I know we have a whole class, Ag 225, that talks about that, so I'm not going to talk about that in this class. And superconducting magnetic, that's pretty exotic and not very mainstream at all. So I mentioned a little bit about it last time, and I won't say much more about it this time. All right, so we're going to talk about a few different types of energy storage today. And remember, batteries are kind of in between. They're kind of like a jack of all trades, master of none type situation. So batteries are pretty decent at a lot of different things, but they're not terrific really at any one individual thing. So that's why batteries tend to be a pretty good application for a lot of different scenarios. But for some things, there are better applications. So today we're going to talk about flywheels, and we're going to talk about compressed air, and we're going to talk about gravitational energy too, and that's not on here, but we'll talk about that at the very end also. So these are all parameters that we should care about if we're thinking about energy storage systems. And two of the most common ways that we measure the performance of energy storage systems are with energy density. A reminder that energy density deals with the volume of the energy storage device. So that's the amount of energy per unit of volume, per meter cubed often. And conversely, we have the specific energy, also known as the mass energy density. That's the amount of energy that you can store per unit mass of the system. So sometimes you care more about one than the other, and we talked briefly about that last time, a few cases where you might care more about one than the other. Okay, so let's start talking about flywheel energy storage systems. The idea behind a flywheel energy storage system is that you have a rotor or a flywheel that is spinning really fast inside of this casing here. And this is a picture of a couple of them. There's a person for some scale. So these things are relatively large, you know, not like the size of a house or anything, but these things are, you know, the size of a person or a bit larger than a person. And the flywheel inside of it spins really fast, up to, say, tens of thousands of RPM. And usually inside of here is drawn at a vacuum, in order to minimize the air resistance inside there. And basically what you do is that you spin this up to a very fast speed to charge it, and then to discharge it, you're using some of that really fast rotation speed of the rotor, and you're going to convert some of that rotational kinetic energy into electricity. And the way that you do that is you have a device called a motor/generator, or a motor generator. And I'm pretty sure I've mentioned this before, but the cool thing about generators is that they can usually, most types of generators can be used as a motor, and most types of motors can be used as a generator. So we're actually going to use this one electrical device as both a motor and a generator. That would probably be somewhere inside the device. It would be like either at the top or the very bottom of this device. And when we want to charge up the device, we use it as a motor. So we're feeding electricity to the motor, and the motor is accelerating the rotor or the flywheel inside there up to a really fast speed. It would likely be doing that when electricity is cheap, you know, like in the early hours of the morning. And then when you want to discharge it and convert that rotating kinetic energy that's stored into electricity, you use the electrical machine as a generator, and then your force that's causing the generator to rotate is the flywheel, and your output is connected to the electric grid. So you're using one device as both a motor and a generator. This company is called Beacon Power. They're a pretty big player in the game of flywheels. They're based in Massachusetts. They've had a kind of an up and down history, as a lot of these energy storage companies have. Even battery manufacturers are kind of constantly consolidating and reorganizing, and there's a lot of upheaval in the energy storage market. So They did at one point actually declare bankruptcy, but they are back and they still exist as a company and they're still doing projects, although not at the same scale as, say, battery storage projects are. Okay, so here's the basics. I probably said a bunch of this already. So we're storing energy in the form of rotating kinetic energy. We've got the rotor, aka the flywheel, in a vacuum to minimize the friction so that you don't have any, or you minimize the amount of losses that you get to the system. They can also use maglev, magnetic levitation, which again minimizes the friction that you might have in bearings. So that's a nice component that some of them will use. They can go really fast, 50,000 RPM. It's kind of hard to imagine something spinning that fast. That is a incredibly fast rotation speed. So because it's spinning so fast, there are a lot of stresses in that flywheel. And so they tend to use very kind of fancy and very high strength flywheels or rotors, like made out of composite materials. So basically this is what I just tried to describe. When you're accelerating it and you're trying to store more energy in it, you have a motor generator that acts as a motor and it spins up the rotor to a higher speed and therefore it's converting electrical energy into rotating kinetic energy. Then when you want to discharge it, let's say between 2 p.m. to 7 p.m., something like that, then the electric machine acts as a generator and it's converting the rotational kinetic energy into electrical energy. Obviously, there are some losses associated with that. You know, it's not a perfectly efficient machine. So you're taking energy from the electric grid, converting it into rotating kinetic energy. There's going to be some losses associated with that transfer. And then when you want to, you're going to convert that rotating kinetic energy back into electricity and put it back on the grid. But there's going to be some efficiency losses with that. All right, the way this usually works is that you have a converter that is attached to the motor generator. So this is the motor slash generator that we were talking about. And the type of converter that it uses is a full converter. So this is why I like doing that discussion of the different types of renewable energy generators, like we talked about, about a week ago or so. We have the type A, type B, type C, type D machines. And this is a type D. It needs to be a type D because the type D uses a full converter. And the advantage of the full converter is it doesn't matter what the frequency is over here, right? So it doesn't really matter what rotating speed this is going to rotate at, which is good because this could be rotating anywhere from a couple of hundred RPM on the low side up to tens of thousands of RPM on the high side, right? So this is rotating at a very variable speed. Because it's rotating at a variable speed, the output of this generator is going to have highly variable frequency, right? So this is going to have highly variable frequency when this is operating as a generator, right? And we want to produce over here, we want to produce nice, clean, perfect 60 hertz AC. So the way to do that is to use a full converter. So all of the power output from this generator goes into the converter. It gets rectified into DC, like it says right here, and then it gets inverted into nice, clean 60 hertz, or 50 hertz if you're in other parts of the world. But in North America, 60 hertz AC electricity, and then through a filter, and then goes on to the electric grid. All right, so it needs to use that full converter because we don't know what this frequency is going to be right here. And we don't know what this frequency, frequency of this electricity right here is going to be because we don't know what the frequency of the rotation speed is. Is this going to be operating at 1,000 RPM or 50,000 RPM? It'd make a big, big difference in the frequency of the output right here. All right, here's some equations that you're going to use to solve some problems. There's nothing too tricky or too fancy here, but This is important to doing some kind of back of the envelope calculations for flywheels. So the equation in the red box obviously is the most important one. And you can see that it's very similar to the basic kinetic energy equation that you probably know and love, which is kinetic energy equals 1/2 times m times velocity squared. That applies to basically any moving object that I would, throw across the room. If I know its mass and I know its velocity, then I can use this equation and calculate its kinetic energy. So it looks very similar to the kinetic energy equation, which is not surprising because it is kinetic energy, but it's rotating kinetic energy. It's in a different reference frame. And so the equation is just slightly different. We have to modify things just a little bit. First of all, we have the angular velocity, omega. That's a lowercase Greek omega, replacing the velocity. It's still squared, so we take the angular velocity squared. And angular velocity always needs to be in radians per second. All right, so when you plug into this equation, make sure that omega, angular velocity, is in radians per second. So we don't usually talk in terms of radians per second, not usually. If we're talking about the rotation speed of something, usually it's more convenient to say RPM is probably the most common one, revolutions per minute. You could say revolutions per second, but RPM is probably the most common. So you'll need to do some conversions here. If you're given that the rotation speed of the flywheel is 10,000 RPM, revolutions per minute, you're going to need to convert to radians per second. All right, to do that, you need to know that one revolution is equal to 2 pi radians. All right, so convert from revolutions to radians and convert from per minute to per second so that you end up with radians per second. All right, I'll do an example problem here in 1 or 2 slides, but keep that in mind. That's what we're going to have to do. So omega is going to be in radians per second, and I is something that takes the place of m, and I is called the moment of inertia. All right, and that you might not be real familiar with that. That might not be an intuitive thing. I'm going to switch over to the document cam real quick. I'm going to show you kind of a virtual experiment that kind of gets at moment of inertia. So let me switch over. All right, here's what I want to show you about moments of inertia. So I'm going to give you 2 kind of virtual experiments. So let's think about 2 identical ramps. All right, so here's a ramp, and here's a ramp. And they're supposed to be identical. All right, so this angle, whatever it is, theta, is equal to this angle, whatever it is, theta. And they're totally identical ramps. All right. And now our experiment is that on this ramp, we're going to have a solid disk. All right, so I'm going to draw the side view. So the side view of a disk is just a circle. So this is our disk, and it's a solid disk. And it's going to race down the ramp, and it's going to race against something that has the exact same radius, exact same diameter, except it's not a solid disk. It's more like a donut. All right, so this has the same, I'll just say the same dimensions. That way you know it has the exact same radius, diameter, depth, all of that are the same. And this is also important, it has the same mass. All right, so even though this has a lower volume, right, it must have a lower volume because it has that hole taken out of it. The donut hole is gone. So this must have a higher density than this one does, but they have the same mass. So they have the same dimensions, I guess, except for the inner radius here. So overall, the same radius, same diameter, same depth, and they have the same mass. And one of them is a solid disk, one of them is like a donut shape. And we're going to race them down to the bottom here. All right, so I don't know if it's probably not real intuitive, if you were to guess which one is going to go faster down to the bottom. But I'll tell you that the one that's going to win 10 times out of 10, every single time, the one that's going to win is this one. The solid disk is always going to win. Win the race. Which one? It's always going to be the solid disk. It's never going to be the donut. All right, but I'm going to do kind of opposite experiment. So that was one experiment. We know that that one is going to accelerate faster, and it's going to win the race. It's going to win the race. All right, we're going to relate this to moments of inertia in just a second. But now let me, let's see, what can I do to do the other experiment? So let's say that I have, this will work. Let's say that I have a flat ground with some rolling resistance. So let's say that we've got like grass here. All right, so we're going to roll these along this like flat surface. And the flat surface is like grass or astroturf or something like that. The point is it's not frictionless, okay? So it's, as it's rolling, as it's going to roll along here, it's going to be losing energy, all right? So here's our solid disk. Here's our donut. And once again, they have the same dimensions, they have the same mass, and now it's important that we say initially these have the same velocity. So initially let's say we started these rolling at the same velocity. So this is going 10 meters per second rolling this way, and this is going at the same 10 meters per second rolling this way. So now the question is, this is kind of the opposite question from above. The question is, which one will go farther before it stops? They actually will not go the same distance. One of them will go farther than the other. Which one rolls farther before coming to a stop? And the answer to this one is actually the donut shape. The donut shape. Donut. Sounds delicious. Anyway, back to this. The question was, which one's going to roll farther before coming to a stop, given the same velocity, the same dimensions and stuff? And the answer 10 times out of 10 is going to be this donut shape, all right? And the reason for both of these is because the donut shape has a higher moment of inertia. The donut shape has higher, I'll write it out. I'll write it out this time. Moment of inertia. And the variable that we use for that is I. All right, so this kind of makes sense. Moments of inertia is kind of like the rotating inertia that something has, right? What is inertia? Inertia is the resistance to changing its momentum. All right, so that's what inertia is. So this is the resistance to changing its rotating momentum. All right, so initially in this example, they were both stationary, and we're going to race them down this ramp. This one had a higher resistance to changing its rotational momentum. All right, because it has a higher resistance to that, to starting to rotate, it has a higher resistance to getting more momentum. This one has a lower resistance to gaining momentum, and so this one accelerates faster, and it wins the race down to the bottom of the ramp. All right, so this one wins the race because it has a lower moment of inertia, and therefore it can accelerate more quickly. This is the opposite, though. If they're going at the same velocity, all right, so it didn't take the same amount of energy to get these going at the same velocity. All right, so just let me be clear about that. It took more energy to get this one going at the same velocity, v, as it took to get this one going at that velocity, v. All right, but that's not the point of this experiment. The point of this experiment is to say we got these two shapes, They both are going at velocity v, whatever that is, and however much energy it took to get them there. But they are now both going at velocity v. Which one is going to roll farther? The answer is the donut one will roll farther because it has a higher moment of inertia. Therefore, it has a larger resistance to a change in its momentum. So once it starts rolling, it has more resistance to slowing down than this one does. This one has a lower resistance to slowing down, which is because it has a lower moment of inertia. And you can kind of think about that, you know, if that's not entirely intuitive, you know, here's our disk and here's our donut. And remember, we said they have the same radius, same diameter, same depth, and same mass. All right, and that's all those are critical because they have the same mass. So mass m. And so if you think about it, then all of the mass m here is kind of around the outside, right? And it's rotating around this center point right here and around this center point right here. So kind of think about the concept of torque. The torque is the force times the distance from the axis of rotation. And here we have all of that mass that's far away from the axis of rotation. Whereas here we have a good chunk of that mass that's real close to the axis of rotation. So it doesn't take a lot of energy to get this part of the mass that's real close to the axis of rotation. This part right here, it doesn't take a lot of energy to get that part accelerated to a higher rotational speed. All right, it's this part out here by the perimeter that is far away from the axis of rotation that it takes a lot more energy to accelerate to a higher rotational speed, and which has more resistance to slowing down. So the more mass that we can get farther away from the axis of rotation, the higher the moment of inertia, and the more energy we can store per unit of mass. All right, so for a given unit of mass, we'd like to get it farther away. Obviously, we can't have this truly hollow. You know, we got to have at least some support in there. You know, because the motor is going to be trying to spin this up, so it's got to attach somewhere. So it's probably not truly hollow, but you might have minimal support inside here, and you try to get your mass as much as possible. Get your mass around the outside perimeter. All right, so hopefully that was a decent explanation of moments of inertia. With that, I'm going to share my screen again. Okay, here we are back at the same slide. Here we go. All right, so when we calculate the energy stored in a flywheel, it's equal to the moment of inertia times the angular velocity squared times 1/2, and that 1/2 just comes from here. All right, so now we kind of know what moment of inertia is, but we need to know how to calculate it. So this is kind of what I said before. Moment of inertia is a body's resistance to angular acceleration or deceleration, which also means a change in momentum. All right. So this is the calculation that you need to do to calculate I, to plug in here for I. I is equal to K, which is a shape factor times the mass of the flywheel times the radius of the flywheel squared. All right, and your shape factor, you can calculate these, but I'm not going to ask you to calculate K. I'm just going to give you 5 different values of shape factor, and you'll need to apply these as necessary. So if I have a solid uniform disk, that's the first one that we talked about a minute ago. The shape factor for that is 0.606. If you have an ideal donut, and an ideal donut has all of its mass at the perimeter. So in reality, it's basically impossible to have all the mass at the perimeter and none of the mass in the middle. That's impossible. But we can kind of say that certain things are close enough. You know, like a bicycle wheel is pretty close. You know, almost all of its mass is at the outside. It's not exactly at the outer perimeter, but it's pretty close. And so for something like a bicycle wheel or something that's a donut shape where most of the mass is on the outside, we can say that the shape factor is equal to 1. So that's as high as it can get. There's nothing that's going to be higher than that. If you have a solid sphere that's solid all the way through the middle, has a shape factor of 0.4. A hollow sphere has a higher moment of inertia, just like the donut had a higher moment of inertia than a solid disk. So a hollow sphere has a shape factor of about 0.67. And if you have a rod spinning about its center, so that's like this. All right, so that's a rod spinning about its center like that. All right, not like this, because if it's like this is like a solid disk. You see what I'm doing? I'm rotating it like this. So that's just a solid disk rotating about its center. What I mean by this one here is it's rotating about this axis like this. All right. So those are the 5 cases that you might get and you might need to be able to use to make some calculations. Okay, so here's an example. Let's calculate the stored energy in this flywheel. It's a solid disk. It has a radius of 30 centimeters, a mass of 40 kilograms, and it's currently spinning at 10,000 RPM. So we know we have our equation, 1/2 times moment of inertia times angular velocity squared. And we're going to need to calculate what is the moment of inertia and what is the angular velocity squared. So we need to find out what the angular velocity is. So remember, angular velocity needs to be in radians per second. And we were given the angular velocity in revolutions per minute, RPM. So we've got 10,000 revolutions per minute. We got to convert into seconds. We can do that first. So we convert into revolutions per second by taking it times 1 minute per 60 seconds. So minutes canceled out here and here. And we're left with 166.67 revolutions per second. Now we want to get into radians per second, and we've got revolutions per second. So remember, there's 2 pi radians in 1 revolution. So to convert from revolutions per second to radians per second, we got to take it times radians per revolution. That way, revolutions cancels out here, and we're left with radians per second. So we get 1047.2 radians per second. So that's omega that we need to plug in here, and we need to square it when we do that. To get the moment of inertia, we have our equation for moment of inertia, K mr squared. K is the shape factor, and if I go back, shape factor for a solid uniform disk was 0.606. So that's where that comes from. Our mass was 40 kilograms. And our radius is 0.3 meters, and you got to square it. All right, so be careful how you do this. Don't take that, and then square that. No, take this, square it, and then take that result times that and that. Remember your order of operations. So when you do that, you get 2.18 kilograms times meters squared, which sounds like a weird unit, but that's correct. That's the correct unit for moment of inertia. You'll see how these work out in just a minute with the units. So there's our moment of inertia. There's our angular speed. And so we can plug those in. 1/2 times I times omega squared. And we're left with kilograms times meter squared per second squared. I know this is really weird to think about, but radians, they actually don't really count as a unit. I know that's kind of weird to think about, but they don't really count. So what you're left with is kilograms times meter squared divided by second squared. And you may not remember this, but if you Google what a joule is, there are several different definitions of a joule. And a joule is a kilogram times a meter squared divided by a second squared. So if you do this calculation, remember you got to square this number, and then take it times this, and then take it times this. And you'll get about 1.2 million joules, or 1.2 megajoules. All right, so that's our calculation for flywheel energy storage. A few things to remember for all of the problems that we'll talk about today. Remember that work is the change in energy. That's the amount of energy that was added to or taken away from the system. And the amount of work is equal to the energy at time 2. So this is energy at flywheel time 2 minus the energy of the flywheel at time 1. All right, so you can think of it like final energy minus initial energy. So that's the work. And now once you have the work, remember that the power, either the power in or the power out, is equal to the work divided by the time. Pros and cons of flywheels. Some good things are that you can charge it very rapidly. You can bring it up to speed in a matter of minutes usually. It has a high power density, so you can turn that into a very powerful generator, and you can take power out of that very quickly. Just like you can charge it rapidly, you can discharge it rapidly also. Cycle life can be very, very high because you're not really you're not degrading it as you charge it and discharging it. You're not really degrading the system in the same way that batteries do. Batteries do degrade a little bit every single time you charge it and discharge it. So you're only ever going to get, it depends on the chemistry of the battery, but you know, a lead acid battery, you might get 500 charge discharge cycles. For a fancy lithium battery, you might get 10 or 20,000 charge discharge cycles, but it's always limited. And every time you charge it and discharge it, you degrade it a little bit. Another advantage that it's not really affected very much by temperature, whereas batteries are. Batteries need to be kind of within a relatively narrow window of temperature, or else you can either damage them or they just won't. The chemical reaction will not proceed quickly enough. So batteries work best within a pretty narrow range of temperatures. And that window is usually around temperatures that humans are comfortable working in. So that is convenient about batteries, but batteries suffer greatly if you take them below, say, about the freezing temperature, or if you want them to work at above, say, 100 degrees Fahrenheit. Their performance suffers significantly. Disadvantages of the flywheel: low energy density. So even though you got a lot of power out of it, right, you can charge it and discharge it very rapidly, but you can't store that much energy. It's just very difficult to store a lot of energy. So what they do, you may have seen this in the first picture that I showed, you can have flywheel farms. This is a flywheel farm. And so you can see each one of these is installed here, and there's, I don't know, I haven't counted them, but there's probably 50, 75 or so of these flywheels at this flywheel farm. And that's how you can get more energy out of the flywheel, by putting it into a flywheel farm. Okay. There are some standby losses. You can minimize those by drawing a vacuum on the flywheel and by using magnetic levitation, but you're still going to have some standby losses, you know, in the generator, and you can't get rid of everything. So there are some standby losses. It can be dangerous. You know, when you're talking about something spinning at potentially, you know, 40, 50,000 RPM, and that thing that's spinning has a certain mass, you know, it might be 100 kilograms or 200 kilograms, that can be dangerous. You know, if something fails, it will more or less explode. So you don't want to be standing next to a flywheel if it were to explode or fail. I haven't heard of that happening, but it's definitely a concern that has to be taken into account for flywheels. So usually the casing structure has to be strong enough to contain the flywheel if it were to fall apart. The last thing here is that it's difficult to use these for transportation, like say for a vehicle, because of the gyroscopic effect. And so what would happen is that if you had this thing rotating, inside of a vehicle, it would be very easy to turn one direction, but it would be very difficult to turn the other direction. I'm kind of wondering, this is a well-known challenge for integrating flywheels into vehicles, but I'm thinking that you could probably alleviate that if you had two flywheels rotating in opposite directions. You could probably get away from this problem. But I've never built a flywheel car. It'd be kind of interesting, but I've heard of people doing it, but it's not very common. All right, our next topic is going to be compressed air, or some type of compressed gas, but air is our most plentiful gas, so we may as well use air. All right, so this is a machine that's going to do the compression, and then once it compresses the gas, and then if you want to use that gas, then you turn around and you use the compressed gas to drive a turbine, which then drives a generator. All right, so we pressurize the gas or the air into a pressurized fluid inside some kind of pressurized reservoir. So this is potential energy. It's really kind of like pumped hydro because hydro uses a fluid. Air is also a fluid. And so with pumped hydro, you're using gravity to pump the fluid up to a higher state of potential energy due to gravity, gravitational potential energy. With compressed air, you're compressing it, so you're storing that energy. It's still potential energy, but it's in the form of compression, of pressure. All right, so fundamentally, it's kind of similar to pumped hydro a little bit. All right, so we're compressing the air via a compressor. We're storing it in a pressure vessel. Usually that means an underground cavern, just because you need a lot of volume. We're talking a lot of air that needs to be compressed and stored. And so usually a tank, some type of tank that you can imagine, it's just not going to be big enough to make it economical. And so to make these things economical, it's got to be a large volume, which usually means some type of underground cavern, be it natural or potentially man-made. I've heard of like salt caverns being used for this purpose, but so it could be kind of man-made, like a mine of sorts, but it's usually some kind of an underground cavern. There's different kinds of compressors that you can use. It could be a gas turbine that compresses it, or it could be an electric motor that compresses it, that uses the grid or renewables, but you got to have some way of compressing, which is like a pump. It's like a pump / compressor that forces that fluid into the high pressure reservoir. And then to discharge it, the pressurized air goes through a turbine, which spins a turbine, which spins the generator, much like we've talked about before. But one thing that we haven't really talked about before are the thermal issues that come along with compressing or expanding a gas. So it's probably intuitive. You probably would guess that if you compress a gas, the temperature is going to increase, right? Because all those molecules are bumping around next to each other. They're closer to each other, so they're hitting each other more frequently, and the temperature rises, right? So they have more thermal energy. So you got to do something with that heat. You can do something useful with it. You can maybe use it for like district heating, like building or community heat, or you could drive a steam system actually, like combined cycle type steam system, where you're using the waste heat to drive a steam cycle, boil water into steam, and then steam drives a turbine, which spins a generator. Or if you can find a way to store that waste heat as you're compressing it, you can use that heat to reheat the gas upon expansion, because that's the flip side. So it makes sense, it's more intuitive probably, that when you compress the gas, the temperature rises. What may not be quite as intuitive, but it's definitely true, is that if you take a gas and you expand it, the temperature decreases. And that can be a real problem if there's any moisture inside of that gas. And it's air, and it's inside a natural cavern, so there's gonna be natural moisture inside that air. So what's going to happen as you expand that, the moisture inside that is going to freeze, and that's going to clog up the pipes, and then the whole system comes to a stop. So you have to add heat to the system, to the air, as you're expanding that gas. So if you can store it somehow to reheat it on expansion, then you can just use that. Otherwise, you have to use some type of a boiler or electric heat or something to actually add thermal energy to the system upon expansion. So that's a drawback. Usually, like I said, these need to be underground just because they're so big and so massive, and a tank, you know, a pressure vessel tank just is not gonna make it economical. It would work, it just wouldn't be economical. So salt caverns where we've like mined out the salt, or cave formations. Here's an idea. I haven't seen anybody doing this, but you know, we've got a lot of natural gas reservoirs that we're tapping, you know, in various places around the world. Also coal mines. So this is really just kind of some food for thought, but maybe in the future, maybe some of those tapped out gas reservoirs or coal mines could possibly be used for energy storage systems at some point. The difficulty here, well, I'll talk about pros and cons in a minute, but one big disadvantage here is that the soil and ground and rock conditions need to be such that you're not going to get much leakage out of the system. So maybe a little bit of leakage might be okay, but if you get too much leakage, then obviously it's not going to work. You know, if your pressure vessel is not leak proof, then it's just going to all leak out. It's not going to drive the turbine, and the whole thing's not going to work. That's a big problem, is finding formation like rock and soil formations that will actually work for this. Most won't. Most of the time, your caverns are not going to work. All right, so some equations here. I think most of these equations are a little more intuitive. The energy that we can store inside any pressure vessel is equal to its pressure times its volume. And another definition of a joule, its equivalent to another definition of a joule, is a Pascal. That's a unit of pressure. That's 1 Newton per meter squared, times 1 meter cubed. That gives you 1 joule of energy. And this pressure, this P is the same as this P. That pressure is relative to atmospheric pressure. All right, so we know that atmospheric pressure is not 0, but we need to define our pressure of the system in relation to or relative to the atmospheric pressure, because we're starting there from atmospheric pressure, and then we're compressing it to the higher pressure, and then when we discharge it, we're releasing it again, not to 0, not to space, but rather to atmospheric pressure. You got to define the pressure of the system relative to atmospheric pressure. All right, so we need to keep track of our signs here, and we're going to define that work that's done on the compressed air energy storage system to charge the system, compress the gas, is equal to the final pressure times the final volume minus the initial pressure times the initial volume. But kind of like in generators when we said the area of the armature doesn't change, here we can say the volume of the compressed air energy storage system, the volume doesn't change. It's the volume of the pressure vessel or cavern, whatever it is. So we can factor out V1 and V2 and just say that we can simplify this into this. So it's the volume of the vessel or cavern times the final pressure minus the initial pressure. So note that if P2 is greater than P1, I'm going to get a positive number here and a positive number for the change in energy. So when the change in energy, or the work, is greater than 0, by definition, we say that work is done on the compressed air energy storage system. That means we're compressing the gas. And the opposite is true. If P1 is greater than P2, this is going to be a negative number. which means our change in energy and our work is less than 0. And that means work is done by the system. That means it's expanding and driving a generator. So we're discharging. Once again, remember that power is equal to the change in energy or work divided by change in time. Okay, so just substituting this in for our change in energy. Here is an equation for power. And just like before, we can say that if P2 minus P1, remember these are pressures, all right? Don't get confused. This is not power. These are pressures. If P2 is greater than P1, then the power is greater than 0, so we're charging it. We're compressing the gas. And if P2 is less than P1, this will be negative. Power is less than 0. So now power is applied by, or we're discharging the compressed air energy storage system. Pros and cons here. So potentially these can be very large systems. So you can get a lot of power and a lot of energy, both, out of these types of systems. And in practice, you're not going to do this unless the reservoir itself is free or at least very cheap. So you're not going to, you're not going to use something that you're not going to go out and dig a big hole in the ground and use that as a reservoir. It just wouldn't be cost effective. So usually this is done with mines or salt mines or salt caverns, something like that. The dislocations, this is a really big one. There aren't that many locations that are actually suitable for this because there aren't that many locations that have natural caverns that would be useful for this. And even the ones that do exist, they don't always hold air very well. This reminds me, near where I grew up in central Iowa, there was talk in the mid 2000s, like around 2005 to 2010. There was a lot of excitement. They were going to build one of these because there were some natural caverns in central Iowa that had been discovered, and they were going to use this. But that project lasted a couple of years before they realized that it was not working because they would lose a lot of the compressed air that was stored in there. So it was a terribly inefficient system because they were losing too much and they couldn't discharge enough to make it worthwhile. The equipment, you got to get a big compressor, and then you got to get a big turbine and generator that can be used with this compressed air, and you got to heat it in the process as it's expanding. So it can be expensive to build and maintain. And I've mentioned this before, these are big systems. It just doesn't make sense to do this on a small scale. So if you're doing this on a big scale, it could make sense, but if you're doing it on a big scale, that means that there's a large upfront capital cost to buy this equipment. And you got to have it in a special location, in a big cavern, something like that. Okay. All right, the last one we're going to talk about is gravitational energy storage systems. So I would probably actually lump pumped hydro in with this, even though I'm not going to talk about it today, because I think you talked about it at least a little bit in TEC 160. But this is pumped hydro would also be a form of gravitational energy storage. It's using gravity to do work for us and then turning that work into electrical energy. There's something I just find really appealing about this, to be honest, because it's just so simple. It's just like anybody could come up with this, and I like it that way, you know, because it's just so stupidly simple. Like, why not use this type of stuff that, you know, gravity is free, and gravity is always going to exist. So why not use this where we can? Right? So I think that's pretty cool. I'll show you another example of this, but this is a project that is currently under construction in Nevada. Actually, I think there are a couple of them, mostly in California and Nevada, and they're around the mountains. And the idea is that you have basically a train with some electric locomotives. So this is like one electric locomotive. This is another electric locomotive. And this is just for weight, for mass. They're adding these rail cars just for more mass. And so the idea is that at times of cheap electricity, this turns into a locomotive and you drive it up the mountain back here. And then when electricity is expensive and you want to sell it, times of high demand, this becomes a generator. So again, it's like a motor generator. This and this become a generator. And all of this mass from the whole train gets acted on by gravity, and gravity pulls it down the mountain, and we convert that stored potential energy into electricity. Pretty simple. All right, gravitational energy storage, any system that uses gravitational force to cause the motion of the working body, which we can then convert into electricity. So storage is the form of potential energy. So initially, we're to charge the system, we're doing work against gravity. So we're converting electrical energy into mechanical potential energy. Mechanical, means it's at a height, as opposed to, I don't mean to confuse things, but chemical energy is in a way also a form of potential energy. It's potential. It has potential for those chemicals to interact and release electricity also. But let's steer clear of that. We're just saying that we're converting electrical energy into stored mechanical potential energy by increasing its height. And then in the peak hours, when we want to discharge it, we use the gravity to accelerate the large mass from a high height, a high elevation, to a lower elevation. And we use that to drive a generator or do something useful and get work out of that, oftentimes into electrical energy. So there's actually a lot of different systems that have been proposed that use these basic principles. Pumped hydro is one, like I said. The rail car is another one I've already talked about. I've heard of these proposals where you go into the ocean and you have a barge that has a winch on it, and the winch is attached to a large, like a massive concrete weight, and the weight will pull the rope down, and you can use that to discharge the system. And then when you want to charge the system, you use electricity and you power the winch and you pull the large weight up to the surface, and now you're storing it at a larger elevation, a higher elevation. So that's another example. You can do it in the ocean because it's easy to float a barge out into the ocean, and you can use the depth of the ocean. Or really anything involving lifting, usually a solid mass, but it wouldn't even really have to be a solid mass. I would actually say any mass. Anything involving lifting a mass could be used for gravitational energy storage systems. Equations here, again, these are pretty simple, nothing too wildly crazy here. The energy, I'm sure you learned this in high school, the energy, potential energy, is equal to the mass times the acceleration due to gravity times the height. And once again, note that, well, first of all, let's talk through these. So the mass is in kilograms. The acceleration due to gravity is in meters per second squared. Meters per second squared. And height is in meters. And so when you multiply these together, your units are kilograms times meters squared per second squared, just like this. And this is the exact same thing we said for flywheels, and we said that this is another definition of a joule. So you do this and you get a joule. So we can once again talk about our difference in final energy minus initial energy, and we know that that is our change in energy. So the mass at time 2, the final mass times the final acceleration due to gravity times the final height, minus the initial mass times the initial acceleration due to gravity times the initial height. But notice here that the mass is probably not going to change. Think of like your rail car that you're moving up a mountain, right? Your mass is the same as it started with. Your acceleration due to gravity, you could quibble with this a little bit. The acceleration due to gravity on top of a mountain is slightly different than the acceleration due to gravity at the base of that mountain, but it's not that big of a difference. It's a minuscule difference. So we can say that G2 is equal to G1, which enables us to factor out the m's and the g's. And we can say that the change in energy is the mass times the acceleration due to gravity times the quantity H2 minus H1. And then just like before, like we talked about for the pressures in compressed air energy storage system, if H2 is greater than H1, this will be a positive number, and delta energy will be a positive number. So the work is greater than 0, so the work is done on the system. We're charging it, we're raising it up the mountain. Conversely, if H1 is greater than H2, this will be a negative number. Delta energy and work will be a negative number. So then work is done by the system. We're discharging it, converting it back into electricity. Once again, remember, power is equal to the change in energy or work divided by time. And so we can just plug this term in here for change in energy, and you can use this equation directly if you're trying to calculate power. And once again, if H2 is greater than H1, then your power is going to be greater than 0. We're charging the system. If H1 is greater than H2, then you're going to have a negative number and you are discharging the system. Okay, just remember, H2 is final. At the end of this period of time, that's what your final height is. H1 is your initial. So the way you're going to do this calculation, first you're going to do the calculation from the base of the mountain to the top of the mountain, for example. And you calculate the amount of energy or the amount of power that was used while you were doing that. And then after you've calculated that, then when you're calculating the discharge, now up on the top of the mountain is your initial, and the bottom of the mountain is the final, right? So you look at this usually in two different steps. The step where you're charging it, and the step when you're discharging it. Because if you just, think about this for a second, if you're just thinking about it, well, my initial was the base of the mountain, and then I raise it up and I lowered it again, and my final is the base of the mountain, that's the same height. So you would get 0 here, and you'd get 0 power. But you know that's not true. You know that there was power being used by the system as you raised it, and there was power being produced by the system as you lowered it. So you need to look at it from the change in height, from the base to the top, or from the top to the bottom. Here are a couple of examples. Here's that one that another one. There are a couple of these. This is one that's going to be in Nevada. It's a proposed system. It's not real big, 50 megawatts. And the total energy storage of all these things up on the mountain is 12.5 megawatt hours of stored energy. Here's a totally different thing. This is almost more like pumped hydro. The way this works is this is a big solid piston, probably made out of concrete. So this is made out of concrete. And what's going to happen is that we're going to discharge the system over here. This is for discharging the system. So this big, massive weight of concrete is going to push down on this water down here. This is like a large diameter water well. And it's going to push down on this volume of water, and the water will be displaced. The water will come through this pipe and then go through this pump / turbine, and that will produce electrical energy. So we're using gravity to pull down on the concrete. It's going to displace the water. The water comes through here, spins a turbine. The turbine spins a generator, and we're discharging and producing electrical energy. The flip side of that, now my concrete piston is down at the bottom of the well, and I want to charge the system back up. So you use this as a pump, but you're applying electrical energy, and you're using it as a pump, and you're pumping the water from here down to the bottom, and you're going to slowly move that big heavy concrete piston back up to the top of the well. That's kind of cool. I think it's kind of neat. It would. I've never actually heard of this one in operation, but again, I'm really kind of attracted to the idea. They're just so stupidly simple that it seems neat. I don't know. I really like these. I really like gravitational energy storage systems. You know, in general, I like. Well, I don't know. You know, I have mixed feelings about this. I like this kind of goes back to my feelings about solar and wind. I love solar and I love wind. I love both of them, but for different reasons. I like solar because there's no moving parts and there's almost nothing that can break. I mean, I guess if you have hail, you know, never say never, but there's very little that can break in a solar system. But then again, I love wind turbines because they are pretty complex and there's lots of moving parts and there's lots of stuff to study and look at. So they're very cool also. So in my view, the way I think about this is kind of more the way I view solar. Like there's just not that much to fail. You know, don't get me wrong, there's stuff that could fail. You know, we've got some electrical components in here, we've got motors, we got some generators in here that certainly could fail. But it's just using gravity, you know. It's like why not? Gravity is there. We may as well use gravity to even out our electric loads. All right, pros and cons of gravitational energy storage. There's potential here for large power and energy capacity. You know, like kind of like I showed for flywheels. If you want a lot of energy, then you could have a bunch of these, a bunch of rail tracks, or you could just add rail cars here, like I showed initially. Just add a bunch more box cars filled with lead, you know, or something. Anything to add mass. Concrete chunks, torn up old pieces of highway, whatever. Anything to add mass. Power, you can just use a larger motor generator. You can get more power out of it. They're relatively simple. This is what I was saying. They're like almost stupidly simple and relatively cheap. There's not that much that's complex here, so they tend to be fairly cheap. All things considered and relative to other types of systems. The dislocations are, you're going to need a special location, depending on what type of system. So this type of system with the well, you probably could do this in Illinois. You probably could make a system like this in Illinois. A system like this, maybe not, because we don't really have mountains around here, or even sizable hills to speak of. So this probably not going to work very well in Illinois. You could do something similar, like maybe with a big tall platform and use a winch like I was talking about before and have a big mass that you either pull up to the top or you're discharging and letting it fall down. That would work, but the rail car system probably won't work in Illinois. So maybe for some types it would require a special location. And this is also true once again, like this generally works best for large systems because you have a pretty decent amount of fixed cost, upfront cost, capital cost, like to buy the motor generator, to build whatever type of infrastructure you need for this system. So it's a lot easier to deal with that upfront cost if the system is a large system. The economies of scale work out better. All right, last word here. That's the three different types of energy storage systems that we're going to talk about in this class, besides batteries that we talked about last time. Just a last little comment here about efficiency. So even though we are talking about taking electricity from the grid, storing it for a while, and then returning it to the grid, obviously it's not going to be 100% efficient. You're going to have losses when you charge it up, and you're going to have losses when you discharge it. So you'll have losses on both sides, when you charge it and when you discharge it. So nothing's going to be 100% efficient. Your efficiencies are going to vary by the type of system, you know, whether it's batteries or compressed air or flywheels. And even then, it varies by the type of compressed air system and the type of flywheel system and so on and so forth. So generally at least 50%. If you're not getting at least 50% efficiency, probably not going to be cost efficient. And some of them can be greater than 90%. Batteries can be greater than 90%. Yeah, a lot of these can be greater than 90% in that ballpark. All right. So efficiency, the definition of efficiency, once again, this is the Greek letter eta. We talked about that earlier on in the semester. Efficiency, eta, is always equal to the energy out divided by the energy in. So what do you get out? What's useful? What useful output do you get from the system compared to what did you have to put into the system? So energy output divided by energy input, or you can also say it's work output, useful work output from the system divided by how much work you had to put into the system. All right. And once again, you need to divide this up into charging efficiency and then discharging efficiency. All right. So if you want to talk about the round trip efficiency, the round trip efficiency is equal to the charging efficiency times the discharging efficiency. So let's say hypothetically you had this is not realistic, but let's say you had a system that was 90% efficient at charging and 90% efficient at discharging. I've got my calculator right here. And if I take 0.9 times 0.9, that gives me 81. Yeah, I could have done that in my head, but that means the round trip efficiency, or the efficiency of taking electricity from the grid and then storing it and then putting it back onto the grid, is only 81% efficient. So you have to look at, for the round trip efficiency, if that's what you want to get at, you have to look at the charging efficiency times the discharge efficiency. That gets you the round trip efficiency. All right, so with that,
that should be enough for you to do the very last homework set in this class, which will be due on Wednesday. We'll review it on Wednesday like we always do. So you now have all of the material in TEC 259 because we're not going to cover any new material on Wednesday when we meet on Zoom. So if you want to bring any questions to our meeting on Zoom on Wednesday, that would be good. If you have questions, then probably other people in the class have questions as well. So feel free to bring any questions that you have about anything related to the class, or especially about the second half of the class on Wednesday, and we'll talk more about that on Wednesday. When we meet on Zoom on Wednesday, we'll do a little review session. We'll talk about the material that we've talked about in the second half of the class, and we'll talk about what the second exam is going to look like during finals week. So with that, let me know if you have any questions, as always, and I'll see you next time. Have a good one.